Hello everyone. Welcome back to our philosophical geometry class. Good to see you guys today. Hope everyone's doing well. It's pouring rain today. It has been here in Southern California for a few days now, but it's fine. It's perfect for what we're going to do today, related to geometry and discussion about music and everything. So very excited to have you guys here with me. And again, I just want to thank everybody. It's been amazing how people have sent in their geometric work and everything, and it's been so good. I've been stunned how good people have gotten. I think you guys probably all were pretty expert at geometry before joining this class. So thank you for joining me, even though you're an expert and I'm just still learning here. But there is some new exploration stuff that's happening right now that I'm pretty excited to share with you guys today. And we'll be learning a few new things and how to draw a few new things today too. So that's going to be cool. We're going to learn how to draw the Hexapentakis, and we're going to learn how to draw, first of all, a pentagon. Pentagon is not an easy one to draw. It's strangely more difficult than you would think. And even though I've done it many, many times, I often forget the steps and everything. And it's more easy when you can do it along with a hexagon. So I'm going to show you guys how to do that. I'm going to make sure that our Facebook Live people are on. Hi, everyone on Facebook. So you're probably wondering, what is this thing that I'm showing you now? Yesterday, I showed you guys how to inscribe circles and how to build geometry, and how each geometry successively has nested within it the information you need to make the next geometry, which is really fascinating because that basically says something about consciousness and how geometry acts as if it's its own consciousness, which is pretty amazing. And this is another perfect example of this. And I'm just going to take you through this real quick. And again, for those of you that are on Instagram, if you want to see the best view of this, go on to Facebook Live and you'll be able to see all of this on Facebook Live in really clear detail. So this is basically the same thing that we did yesterday. It's in a slightly different format, but it's basically telling us the exact same message. And what I did here is I started with a triangle, and then from the triangle, I was able to determine, a circle around that triangle. And then it was also able to give me a vector, which becomes an important vector line at the base of the triangle. And this is a totally new thing that I just found today. I didn't really think about this before in this way. And of course, it's got the top line coming off of the peak of the triangle. And then just as we talked about yesterday, you could basically take right at the 30-degree point on a large circle. You could draw a line straight down at that 30-degree point, and of course it would then intersect down here at 150 degrees. And you could do the same thing on the other side. And all polygonal geometry, as they expand to their more complex forms, will end up lining up precisely on this line. And it basically arranges perfectly based on the angle of what's called the arc length of each of the polygonal sides. So for example, here we have straight off of this a 90-degree angle, that would be formed from a horizontal line straight across here and straight up here. So we've got a perpendicular angle here. And this is informing, of course, the arc of a square. So I can now make a square go perfectly within this, and I can basically exoscribe a circle around that as well. Then the next thing is the next place would be right along this line at 72 degrees. And I can show you by measuring this as well. Hopefully I did a good job on this so you can see. Okay, it's lined up. There we go. All right, there we go. So this is basically showing us 90 degrees. There we go, 90 degrees. And right at 90 degrees, we have to use this calculation slightly differently because I'm measuring this from the opposite direction, right? So this would be from here to here would go from 90 to 180 degrees. So if I'm going to subtract 18 degrees off of that, right, off of 90 degrees, this being another 90 down here, it's going to be 72 degrees, right? So this is where the pentagon angle is. And that is the arc length of the pentagon. Then at 30 would be 90 minus 30 is giving me 60 degrees. Let's see if I turn it this way. It still doesn't quite work great, but I think you get the basic idea. So here you go. Here, this works this way. So you got 72 degrees here, now because I've turned it sideways. 72 degrees is the line of the pentagon. The line of the hexagon is 60 degrees. The line of the heptagon is 51.42 degrees. And we got 45 degrees for the octagon. You got 40 degrees for the nonagon. You've got 30 degrees for the dodecagon, and you've got 32.72 for the hendecagon, which is 11 sides. Now, what's really interesting, fascinating to me about all of this is not only does the universe arrange itself so incredibly, but it's just amazing to me that all of this complexity, even though you've got all this complexity, these two lines act like posts. They're like fixed and immovable. They, you know, all the way to infinity, it doesn't matter how many polygonal sides you have, the first top two sides up here of that very, very complex polygonal geometry will fit perfectly right along this line. That's kind of like, what? It's amazing, right? But not only that, and this is what I really kind of had the big aha moment today related to this, as I was redrawing this. What I also noticed is how you've got this incredible symmetry that's coming off of this. And I'd noticed this before because whenever you see people that have drawn this or have done it on a computer, you see kind of this pattern coming off of this. But this also goes infinitely. So literally comes off like this big U shape here. And then it does it again, right? But then here at the bottom, so the triangle also has all these points on them. So basically on numbers like 8 and 12, we're landing exactly on the vector of the triangle, the equilateral triangle coming off this too, which is like, wow, that's amazing. And in addition to that, and it happens of course on this side as well, everything's just mirror reflected across a mirror at center. And then also on the bottom, which is what I hadn't ever noticed before, was that if I draw a line where the pentagon is overlapping the hexagon that's surrounding it, right? Where that overlaps, it also creates a vector line straight down to infinity so that each of these numbers, like this one right here, which this is, I believe, heptagon, right? So this is the hexagon. So you got the square, you've got, and I also drew here, just for reference, I perfectly squared a circle, close to perfect anyway, perfectly squared a circle that is right here, that I had inscribed the triangle within. So that's why you can see up here this section of square that is above the circle, right? And it just so happens that it meets perfectly with where the square that is inscribed within it as well meets perfectly right on this edge. So you can basically exoscribe a circle around it. But what was fascinating to me also is how where this pentagon overlaps the hexagon, I could draw a straight line down, and then for the heptagon, which is right here, right? So here are the heptagon lines. Its angular reference down here, which would be its second, third, the third reference, or the third angle of incidence going around clockwise around the heptagon, is coming up exactly off of this line right here. And the same thing happens again for a nonagon, and the same thing happens for a hendecagon, which is 11 sides. And so this goes, and I've checked, it goes infinitely this direction. And then for all the even numbers, you'll have a peak at the base, and the peak of the base comes right off of the square, or I guess you could have inverted the triangle the other direction and had its apex pointing down, and then it could have gone infinitely like this as well. So you've got a vector that's fixed here, a vector that's fixed here, right? A vector that is fixed here, right? So this was the vector we already studied. This is fixed, this is fixed, this is fixed, this is fixed. These two are fixed. And then you've got these curvy lines, which are, you know, like this U shape here and this other U shape here. And those are also fixed, but they have this spirality associated with them. But these stay completely linear. So that means that we've got, you know, 1, 2, 3, 4, 5, 6 linear vectors and 4 curvilinear vectors, right? So let me count this again. So 1, 2, 3, right? 4, 5, 6, 7, 7, because I forgot to count the one in the center, 7 and 4. Isn't that interesting? So 7 linear vectors and 4 curvilinear vectors. Now, something is speaking to me about this. I don't know, the 7-11 thing, and it's not just you know, an icy that you can get at 7-Eleven. It's definitely sticking in my mind. There's something to this 7 and 11. 7-11. And another number that comes up a lot is 14. So I started adding these up, and I started noticing something very bizarre. So you've got 1, 2, 3, and these are just the lines of vectors, right? So this line of vector, this line of vector, this line of vector, this one, so 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now 14 sticks out to me in a major way. Why does 14 stick out to me so much? Well, because when I was doing all this work on scales in music and using base 9 mathematics, I noticed something very unique about it. Because you can multiply 14 times 9 and it equals 126. And 126 is one of the C notes. It's a C note that is in Pythagorean tuning. So 126, if you use just tuning, 126 hertz doubles to 252, doubles to 504. And 504 in number theory has a very important role. Like life seems to come out of this pentagon. So even before we get all the differentiation and very important stuff like DNA, we see squares butting up against pentagons. And that is creating a lot of the spark of life, I guess. And those numbers match up against the just Pythagorean tuning. So I started looking at this and I'm like, wait a minute, maybe what's really going on here is we have 14 notes in the scale, just as we see, if you keep doubling, octave doubling all of the 14 notes, you'll end up with all the just Pythagorean tuning before equal temperament. And so I'm kind of like going, maybe the reason why there are 14 vectors here is because each one of them is a musical note. Because everything in the universe is music. And geometry is just frozen sound. So, and I'm not ready yet to, stake my claim on this, but I already have done a lot of work on this type of thing. But let's say this starts with A, then this would become A sharp or B flat, then B sharp, then C sharp, D sharp or E flat, of course, E sharp, F. And I've actually made a differentiation here between E sharp and F. That there's a subtle difference, and B sharp also. There's a polarity shift that happens. I think this has something to do with Euler and pi. Because there's this 2/3, 1/3 relationship. So this would be 1/3, and this would be 2/3. And 2/3 times pi plus 1/3 times Euler equals 3. So 3 is this fundamental thing. So there's more to be done here, but I just wanted to let you into the way I was thinking about this. And again, the majestic beauty of this structure is just kind of astounding. That you've got so many fixed vectors, and then all differentiation comes off of this. Isn't that just astounding? It's amazing to me. Okay, so now I'm going to show you something else here. So this became a paper that we published on tuning to the perfect fifth at 432 hertz. And what this is basically showing, hopefully you guys can see this. I'll move this over here. when I first started doing this work, I thought it'd be cool to have this gigantic leather book. I love it, but it's also a pain in the butt because these things knock all my stuff off my table and whatnot. So this was the original work I did, and I did it all in pen, so I had some mistakes and couldn't exactly correct it. And this is before I started doing a lot of geometric drawing and everything, so excuse my kind of messiness here. But what I was basically thinking was, if I took a guitar string, right, and I have this string, and I were going to correlate it against music, right, based on the length of the string. Let's say that the length of the string was going to also be, I could look at it in a circle because everything is circular. Even if I draw a straight line right now, because the earth is moving so fast, what's going to happen to my straight line? It becomes a spiral, right? So nothing is totally straight lines because we're in motion, even though I might look at this ruler and say, well, wait, that's a straight line. Well, not really, because the earth is moving so fast. We're moving at about 1,000 miles an hour rotationally, like a gimbal. And then we're also moving at 66,000 or 67,100 miles per hour as the planet is going around the sun. Okay? And people that would say, oh, well, wait a minute, the earth must be flat, because then all the water would fly off the earth. That is the funniest thing ever. But I'm not going to explain the concepts of gravity here today. Please go back to school and study about Newton and what Newton basically showed on that. And yes, water can stay on the planet even though it spins. It's not that difficult. And like I said yesterday, it's like, well, from your perception, the earth is flat. I mean, it'd be like, imagine if you're a grasshopper. If you lived in a field and you're a grasshopper, your entire universe would be the field. It wouldn't be more than the field. You wouldn't know the flora and the fauna would be only that which you saw and experienced. If you ended up getting reincarnated from grasshopper and you became a monkey and now you're in a jungle, there's a lot more diversity of both flora and fauna. And now you can see all this other diversity, and there's all kinds of other life. There's a lion, or there's a leopard, or there's a sloth. There's all kinds of different life and different, millions potentially of different species of things that you could experience. All very different from the field that you lived in. So then let's say you get reincarnated. Again, even though you lived in the jungle, you never experienced a human city. So now all of a sudden you live in a rural town. And you never have left that town. You never travel. You never go anywhere. That becomes your entire world. That becomes the zone of your perception. Now, as you expand to higher levels of perception and awareness, then you start meeting people from other countries. You start experiencing other things as your expansion occurs. And you might be born again into another life that ends up, being in a big city. And as you expand more and more consciousness, that stuff that you experienced as a grasshopper would be so much more diverse than what you experience now. And things that were just outside of your zone of perception could now be eliminated to your vision and to your understanding. And that's why yesterday, I think one of the people, I think it was Daniel, basically said, oh, I'm going to keep this quote, which I laughed about later, which was, I said, well, when someone basically argues on a point, so very often my response will be, well, in their own perception, they're correct. But sometimes you don't even recognize, in fact, that's the nature of limited perception. When your perception is limited, you can't even recognize that it is limited. That's kind of the point. If you're living in the second dimension, you're not going to ever be able to describe what the third dimension is. It's impossible. There's a great video on this, though, if you look and watch Carl Sagan. If you just YouTube Carl Sagan explanation of dimensions, he explains it very well, and how, even if, if you're a flatlander, you live in the second dimension, if an apple falls through your world, you would only see an apple that would be flat as it fell through your world, right? You wouldn't actually see the whole apple. And if someone actually had the ability to see the apple and described it to you, and you'd never seen it before, you would think they were crazy. Well, maybe that's what people are experiencing when they're having extraterrestrial experiences, or when they're having psychic phenomenon or other things that are just impossible to describe in the terms of the current dimensional frame. So what I have basically done here is tried to look at another dimension of musicality. And where the nexus of that musicality is around geometry. And so I thought, okay, well, let's take a string, right? Let's take a string and let's pluck a string. And then let's say that that string is the appropriate length, right? And let's assume it's 1.718 feet. The appropriate length that would pluck the string and the appropriate tautness, so the tightness that it is, that it would actually resonate at 432 hertz. Now let's say we took that string and we made it a full circle, okay? Now I then wrote a correlation between hertz frequency and also sum of angular, the sum of angles, of interior angles of geometry. And I knew that you could basically take certain things like, the F sharp, and if you watch the sonic geometry film, you'll know what I'm talking about. You could literally say, okay, the sum of angles of a tetrahedron is 720 hertz, 720 degrees. If I double that, it's 1440. So both of those are F sharps if I were to convert them directly into hertz. And then if you go up from there, you have 720 for a tetrahedron, then it's 1440 for an octahedron. Then the next one you're going to have on the list is going to be a cube, and the cube is 2160. So if you know music well, 2160 is actually a C sharp, and the reason you can figure that out, if you have a few of these numbers memorized, you'll know that 2160 is the sum of angles of a cube. You divide it by 2, right? Now you're at 1080. You divide it by 2 again, you're at 540. 540 hertz is a C sharp, okay? So then I've got F sharp, then C sharp, and then I could go to the next level, which is beyond that is going to be a icosahedron. The icosahedron is 3600, so 3600 degrees. So 3600 degrees, if I keep cutting that in half, it's going to basically give me a note that's an A sharp. So basically it goes 720, 1440, 2160, 3600, and then a dodecahedron is 6480, right? So now I've got the platonic solids, all the platonic solids, and they're making for me a 5-part harmony F sharp major chord. And I could keep going up with that. It makes this F sharp major chord, which by the way is a really beautiful sound in music. But I knew that the reference wasn't going to be exactly between hertz and degrees. And so that is a reference point on why structures are the way they are, just like we saw on the geometry. But I wanted to find the exact geometric correlation. And so what I did is I started looking at strings, started having the string. If I have the string of 432 hertz, it's going to double to 864, right? So I wanted to find that exact relationship between the string length, as well as its tautness, as well as its hertz frequency and its angular sum of angles for the polygonal geometry that it's associated with. And this works both in 2 dimensions and 3 dimensions, by the way. And so if I have a guitar string that's this long, have you ever noticed that if you go to about half point on the string, you'll go to the next octave, but there's so many notes. If you had a really thin finger, you could basically go on to infinite number of notes before you even get to the next octave. That's the nature of how octaves work, right? Well, basically, if I've got a guitar string and I go to this point on the string, which would be, let's say this is the end of the fret on the guitar. If I go to this point where this is going to give me the note B. And as you get closer and closer and closer to the near part of the guitar fret to you, it's smaller and smaller moves in order to get higher and higher notes. I'm not a guitar player, but I am a musician to a degree. And I, before I ended up going into business, I was a music major and had a full scholarship and everything. But I gave it all up because I thought I was good, but good enough to get a scholarship but not good enough to make money at it. So I gave it all up. Well, now it's kind of come back to me over this last 8 to 10 years. And what I noticed was that all these notes start to populate on the string in between. So there's nothing fantastic about that, nothing great. But let's assume that we know that 360 degrees is directly correlated to 432 tuning. Now this would be a 5-6 relationship because 360 divided by 5 equals 72, right? 72 times 6 equals 432. So we know this 5-6 relationship is really important. So what I did is I started to build a geometric model around this. Starting with the premise that 360 degrees was equivalent to 432 tuning, I created this map, right? And said, okay, if the degree reference is 360 degrees, that's one turn of a circle. That's giving me an A note in the 5th octave. The length, in this case, it was 12 inches. I multiply that by the multiple of 432, right? Which I'll explain in just a moment. So that's a multiple related to 432. And then the sum of angular reference, right? There's no angles on a circle, but we know that it's 360 degrees. And then the Hertz frequency associated with it, the sound that comes off of that string of this length and of this circular reference, is going to be 432 Hertz. And it's going to give me a polygonal geometry shape, which is right here, right? And then the 3D reference point will be on the side here, and I never finished it totally. I finished it in the paper, though. So basically, you then go to the next arc length around the circle, and I'll explain it in a moment with the picture, is 30 degrees. Then the degree reference point, because remember, it's going the opposite direction. You have to go higher notes. You have to shorten the string, okay? So remember, the string is shaped like a circle in this case, but we're going to move it to a smaller part of the string, just like I was talking about here, right? So here's my ellipse or circle, and I can go to here, and now I'm going to be a B note, and I go here, I'm going to be a C sharp. So then what I found was, okay, so the landing zone will be 330 degrees for this arc length of 30, which would give me an open angle, two-sided polygon, or what's called a diagon, right? It doesn't close. We have to have a B, I mean the triangle will give us a closed note, right? So then you've got, the next point would be against 360 degrees, it's going to be 0.9166 of the circle. I basically shortened the circle to, by approximately 8.5 or 0.085 approximately, right? I've shortened it by that much in order to get to this higher note, the A sharp. So now the length of the string is going to be 11/12, okay? Now against 432, what's happening? It's giving me now 1.0416, right? Is the value that it's going to basically inform. So that means that I've shortened the string, so therefore the Hertz frequency is now going to increase. So now I have a sum of angles still of 30, which is this 30-degree diagon. And then I have a Hertz frequency of 450 Hertz. So 450 is now associating with 330 degrees. 360 degrees associates directly with 432, right? Then I do the same thing and I keep going down, right? So 300 gives me now a 60-degree arc, which of course is going to be informing a triangle, right, on this matrix. And it's giving me 468 Hertz. And again, this is all just tuning. You have to make small equal temperament tuning changes using the Pythagorean comma, which is a value of 1.0136. And then also pi over 3 that relates to that as well, but that's subject of another lesson. And so then we go to 90 degrees. So remember, the circle was the note A. Where is the note C? And I remember being in bands and orchestras, and we would tune an orchestra to A. We would tune a band to C note. And I would always get confused. I'm like, why do we have to tune to different notes, right? Well, actually, it's not so different, because what's happening here, if A is a circle, then C becomes the square inscribed within that circle. That was kind of cool. I was shocked by that. And of course, it happens at 90 degrees, right, which would then be the arc side of the square, okay? So now we're at 9/12, so we've got 12, right, and then 11/12, and then 10/12, and then 9/12. And then the multiple times 432 for my conversion is now going to give me 504 hertz, right? So 504 hertz, I said 504 is an important number, pentagon square, right? 504 hertz is marrying up against a degree reference of 270 degrees, okay? That's giving me now the square. So four-sided square, 504 hertz. Now the next point it's going to go is it's going to land me at 240 degrees, and it goes to then 0.666 of the circle, which is giving me a C sharp, is giving me a value of 8/12 of the length of the string, and it's giving me 1.25, right, against 432. So now that's giving me a value of 540 hertz, is going to be building for me this hexagon. I thought that's fascinating because isn't that interesting? 540 hertz equals a hexagon, even though it's 720 degrees, right, as the sum of its angles, but it is equal to the number of degrees sum of angles for the pentagon. So 540 hertz gives me a hexagon, 540 degrees gives me a pentagon. So there's this 5-6 relationship popping out again. So now you notice it was 11/12, 10/12, 9/12 of the string, 8/12, 7/12. So now let's go to the next level. It's the first time we break this order. Once we break through 7/12, the next one, which was a D sharp, is going to basically give me 6.75. So we just talked about C sharp. Let's go to D. So D would land at its arc reference point is 45 degrees, which of course is going to be an octagon. It lands at 225 degrees. That's 0.5833 of the circle, 7/12, and then 1.333 on the 432 scale. So then that gives me 576. Now what you'll notice is all these numbers are adding up to digital roots of 9. So 4 plus 3 plus 2, 4 plus 5, 4 plus 6 plus 8, 5 plus 4, 5 plus 4, 5 plus 7 plus 6, 6 plus 1 plus 2, 6 plus 4 plus 8, right? And if you end up with a number like 18, that reduces down to 9 again. So now I can keep going, but now I'm making smaller and smaller delineations, right? So now it's no longer inches. Now it's 6.75 divided by 12 is going to give me the D sharp, which is 612 hertz. Then at 15 degrees, this is going to give me a 24-sided Icasi tetragon. And the one before that gave us a dodecagon. So it goes 1, 2, 3, 4, 5, 6, 8, 12, 24, 48, 57. Now this is where it gets really interesting. So you got 6.48. And as I said yesterday, the sum of angles of a 24-sided polygon is 3,960. Now, did any of you guys look it up to see on Google what the radius of the Earth is in miles? We have 24 hours in a day, and the radius of the Earth is 3,960 miles. Mind blower, right? So then you take, and you're now at F. And F lands at 6.24 out of 12 of the string. 684 hertz. Gives me 48 sides, right? Which has this angular reference of 8,280 degrees. And then we're going to go to this one right here, which comes out to be F sharp, the beautiful F sharp, which interestingly has a reference against 360 of 5150. That 5150 is the same as the angular reference of the Great Pyramid. 5150 converts, that's actually equal to phi divided by pi. I talked about this in one of the earlier lessons, equals 0.515036. If I convert that into minutes and seconds of a compass, it comes out to 518436, exactly the slope angle of the Great Pyramid. Now, if I multiply that, right, that 518436 times 360 is going to land me at 186 degrees on a circle, which is, again, a light speed measure. Light speed. If I just take that times 10 to the fifth power, 186, or 1.86 times 10 to the fifth power, equals light speed in miles. That turns out to be 6.18, which is the golden number, divided by 12. has a sum of angles of 9,900, and the Hertz reference now is 720 Hertz. And that has 57 sides. Now, interestingly, I just showed you how the reference here relates to F sharp, relates to light speed. It also relates to phi for F sharp. And now as I look at this, it's giving me a 57-sided polygon. Well, if I take the square root of light speed, the cube root of light speed equals 57. 57 is also the omega constant. It's very close to the Euler-Mascheroni number. So I started noticing, wait a minute, all these notes are inside of here, and then I could take forever and be stuck before I could get to the next octave, right? I have to basically make a leap to get to the next octave. The next octave would be doubling where I was at 432. Now I'm going to 864. And that's exactly half of the string, which was 12 inches. Now it's 6 out of 12. This is not rocket science. And here's how it looks. So this full circle here gives me the note A. And remember what we were doing with the periodic table of elements, it was sine, cosine, sine, cosine. So it goes A sharp, B, C, C sharp, D, D sharp, E, F, and don't get stuck, guys. Obviously, I know that D sharp is also E flat, please. And then F sharp, then G, G sharp, right? And then A again. Now, for there to be a perfect fit of Pythagorean tuning in 9-base mathematics, there have to be 14 notes in the total with 2 gap positions. The gap positions play critical roles, and it's right before the polarity shifts, right before here and right before here. So there's a polarity shift that's happening here and here as you're going around the circle. So just to illustrate, so 360 degrees for A, right? 432 Hertz in music. Now, I shorten the string by 30 degrees, and this is informing for me an angular reference here of a 30-degree digon, which is a 2-sided polygon, right? That not well known by people, but it's like an open angle of 30 degrees. That's the 30 right here. Then it goes, the next note will be another 30-degree jump, and it gives me 468 Hertz. And then 468 Hertz should have another note in between it, because if you notice, this is jumping 18 Hertz, then 18 Hertz. But now the next 18 Hertz doesn't come out to a note that's going to be tunable with other notes in the scale, and it comes out to be 486 Hertz. So that becomes a gap note right before the note C. We don't have a B sharp reference, right? So B sharp becomes a gap, because B sharp is synonymous with C note, right? But actually there's a gap in there, and it's dissonant, it's enharmonic. It doesn't really tune with anything well when you're using this scale reference. Then 504 Hertz becomes C, and that's giving me a 90-degree angle here, which is now informing this square. Now, interestingly, I said that there's a digon here, 30-degree angle here, and then at the B note of 300 degrees, 468 Hertz, I'm getting this perfect equilateral triangle that fits inside here. And you could say that the triangle is the number 3, but it's closed. And so it matches up with the letter B, like a 3 that's closed. So then we're going to go on. So we've got C, which is the square. So of course it doesn't matter what we're tuning to between C and A, because A is always going to have inscribed within it an undertone, right, in some way, shape, or form, of this square, because there's never going to be a circle without its accompanying square. It will always exist. This is when we talk about undertones, people can sing. Some people have the ability, especially you listen to choirs, they can sing and you'll hear multiple other notes, even though they're all singing in unison. And you'll hear them, and this undertone series is a very powerful part of music. So then we're going to go on. So we went from square. So pentagon is where this gap position sits. The pentagon is very hard to draw. I don't know why it's so freaking hard, but it just is. And so where the pentagon is overlapping, right, is always going to be here and here, interestingly. So we've got an upside down pentagon here. That's where a gap note is. So then at C sharp, we're at 240 degrees, which is giving us a side reference of 60 degrees here, which is telling me 60 degrees, 360 divided by 6 is giving me a hexagon. So I have 6 sides. Then I have the D note, which is informing for me the green, which is giving me 45 degree reference, which is a perfect octagon. And then D sharp is giving me the purple, which is giving me a 12-sided dodecagon. And then I've got E, which is giving me 165 interior angle, and that's a 24-sided polygon, right? Then I get up to here until I get up to the note A again, and the octave doubles. And light squeezes out right here at F sharp. Right here. Right at F sharp. So isn't that interesting? So then the next octave happens, right? Now this is no different than the periodic table of elements that I showed you guys the other day, which was this one right here. It's the same thing. Same context, right? This is how the notes work. This is how all the isotopes basically get constructed and built, and the whole thing is built on the same legend of notes. So you now understand how there's a direct correlation between degrees and it's geometric. Because, by the way, if I used 440 hertz tuning, would any of this work to make these perfect geometries? The answer is unequivocally no. I've tried. It doesn't work. So even though you may not be able to tell the difference between 440 hertz and 432 hertz tuning, and there's videos you can watch online and everything that can teach you, and you can listen to the difference. I think 432 hertz music sounds more etheric. But I think more importantly, we know that through cymatics that all of these frequencies are creating geometric structures for us, around us, everywhere. And in fact, that's how the whole universe is suspended in place, is through these subtle frequencies that are basically creating all of the reality that we call reality around us. And the point is that if you have the wrong cymatic frequency, you may not get the right geometry, or you might not have a closed geometry. The geometry may be left open, like it's leaking or something. That is why to switch from 440, it's not because the sound is any better or any worse. I mean, Mozart tuned in 432, Bach tuned in 432. Lots of musicians always tuned in 432, certainly Pythagoras did. And people say, oh, Pythagoras couldn't have known what 432 hertz sounded like, even though he did reference it as beats per second. He downloaded it. That's the way it works. There's a field of information that you can access, because thoughts don't reside in our brains, right? Any one of us can access it. Any one of us can be genius. All you have to do is decide that that's what you're going to do. It's not out of your reach. It's completely within your reach. So once you learn the framing of how to do it, then you'll know generally where you can go and explore, right? But you have to have some basic understanding of frameworks. Otherwise, you'll just end up with like a lot of confusion sometimes, because you can get a lot of information and be like, I don't understand. And then people that only focus in that spiritual realm, right, can like fly away or something. Like they're not grounded. So there needs to be some grounding so you can turn these thoughts into some action or some manifestation, right? So we spent a lot of time today talking about pentagons and hexagons. By the way, you might be wondering what this is. This was me writing backwards. I started writing backwards right before I got all this information. And writing backwards is something Leonardo da Vinci did. And I've done it a lot as practice now. I can tell you, write backwards and in your non-dominant hand, and you will experience something very, very unique about how you perceive the world. So if you're interested more in that, you can study a paper that I wrote on this. And let's get some paper here. And that paper is on my website, robertedwardgrant.com. Okay. So, now, let's start today by learning how to draw. Let's learn how to draw a pentagon. Because I know you guys might think, oh, that's easy, right? No, it's actually not. Let me start with my frame. remember that music and geometry are the same thing. So in fact, you could say that the opposite of music is mathematics. The thing that connects the two together is geometry. Geometry stands at the center, and that's also where language stands. Language is right in between music and mathematics. People that are good at learning languages, it's because they have an inherent ability to bridge the gap between music and math. And language sits right in the center. Just like geometry, because geometry is the language of universal consciousness. Okay, so now we have this circle. We know what to do. We're going to start with drawing a hexagon. And the way we're going to do that is just like how we normally draw our Metatron's cube, right? And the Merkaba. I'll go with a darker pencil for you guys. Make sure the guys can see this. You see it perfectly. Some guy was on here yesterday. He's like, why don't you get a new desk or get some, curtains for your office? It's like, dude, really? That's a new level of entitlement. And I don't have time for that. But the best part about life is when you get to the stage where you don't really care what other people think. Okay, so this is simple, right? You guys are all expert at this now. These perfect equilateral triangles coming off this. Okay, all right, so now let's turn this into a hexagon, because we want this hexagon for its sides. The thing that's cool about the hexagon is that its sides, right, obviously are equivalent to the radius that the circle that is exoscribed around it. So another way to say that would be this distance right here, right, from here to here, right, that's my circle, it's my radius, is going to be equal to the distance from here to here. And this is the only polygon that does that. So it's like some sort of equilibrium balance. Okay, so now we've got a very nice hexagon. Now, what I'm going to ask you to do, I'm going to ask you to draw a line that intersects these two intersections here. Everything in geometry is about finding the relevant intersections that match what you want to do. Isn't that interesting? Kind of a big philosophical thought behind that, because you could say that same concept applies to life in general, doesn't it? Find the relevant intersections in your life, or in your career, or in what you love, and those intersections are the ones that will relate the most to the outcome that you want to achieve. take the paths that have the cross points that are going to match what you want to achieve in life. Okay. So now the pentagon and the hexagon have this other unique thing where they can have these equal sides, right, to each other. And so what I'm going to do is I'm going to basically draw a line. It's going to go, I'm going to draw 2 circles like this, just as if I'm doing a flower of life. Right? I'm going to take these 2 angles right here. I'm not going to do it for all of them, just for these 2. Okay? So now we're going to find out where we're going to place, we're going to build our pentagon. Now, pentagon for some reason is a tough thing to draw, right? But I'm going to show you how to do this. So now you're going to put your ruler on the adjacent peak or point right over here on the pentagon angle. And you're going to have it go right over, right? Not this point, so don't do that. You're going to have it go right over this central point, right? And we're going to then draw a line straight down like that. Okay? You got that? Now we're going to do the same thing on the other side. Okay, everyone got that? Pretty simple, right? Now, we're going to take our compass that has the same side length as the hexagon does, right? And we're going to, it's still the same as the radius, right? Everything matches. Now I'm going to put this right here on this point where there's an intersection. Find the intersection again. I'm going to draw another circle. You don't have to draw a complete circle, but I'm just doing that just so you know, have a reference point on what we're looking at here. And then do the same thing on the other side. Okay. So now the points that you want to remember are this one right here, this one right here, and this one right here. Now from that, I should be able to make my pentagon, right? See, it's weird. It's like an optical illusion to me. Every time I do this, it freaks me out. Because it looks like this is so far afield and it's going to create some weird angle over here that's not going to match the 108 degrees that I want right here, which is what this is, right? And the inside of this, degree right here is 120. So I want to go to 108. So how do I get to 108? Well, this does it for me, even though it fools me every time. Because I'm like, well, that cannot be. It doesn't look right, but it actually is. Now I'm going to basically connect the dots here. Make sure you guys can see this. It looks like you can. I'll move it down a little bit. So isn't that easy, guys? I remember the first time I saw it, I was like, oh, that's so easy. And look, I've got this cool little star that's already been built inside of here too. Right? I could finish out that star if I wanted to, right? I mean, I've got this thing here, this thing here. So now I could finish it out by taking it like this. Isn't that cool? Wow. I've got this perfect like flower-shaped star thingy. Or I could go ahead and put in the pentagram, which is the universal symbol of phi, beyond just the Greek letter. Okay. Look at that. There we go. And I could just keep inscribing within it smaller pentagrams too. So I hope you guys know, just like Da Vinci said, learn how to see. Study the science of art and the art of science. Realize that everything is connected. And randomness is some word that we use when we haven't perceived the pattern yet. Patterns are everywhere, without a doubt. Of course, I could just get smaller and smaller on this, and it goes infinitely. I could do the same thing, of course, on the hexagram. Now, next time, so now you know how to draw a pentagon. Next time, I'm going to show you how I took this mess and found how to use Metatron's cube to draw this, which is a complex job. So look how many lines I had to look through to try to find the lines that would match up against this Hexapentakis pentagon, hexagon. And look, the aspect ratios are even matching, like as if I was looking at this in 3 dimensions. How crazy is that? Like it's bending to the other side. And we're gonna learn how to do that in our next class. We're gonna start going on to some more advanced work as well, but I wanted to have you learn some of the principles of music in today's lesson so that you can basically benefit and see how everything's connected. It's not just geometry that you're putting on paper. It's all around you. It's everywhere. Much love to everyone. Hope you all have a wonderful day. And I'm having fun here listening to this very dramatic Game of Thrones. Have a good day, everyone. Bye.